Okay, so today we're going to go again one step deeper into our topic, into control theory. As I said last time, after having covered all the basics, now we have opportunity to study like more deeply what control is all about. So you remember last time what we did? We asked how can we do the same stuff we did for continuous time systems for discrete time systems, right? We looked at the discrete control, found criteria for stability for discrete systems. Okay, was good. We now know how to talk not only about continuous time systems, but discrete time systems. Okay. Today we are going to do something else. What we're going to do is to ask, is there something better than stability? Is there something better than stability? In fact, when I talk about stability, when we talk about stability, we can think about it as somehow a necessary condition, right? Like we cannot do without stability. If our airplane is unstable, it is almost definitely means it's going to crash, okay? Of course, real life engineering is a little bit more complex than only stability in the sense of a Lyapunov. But still, if the airplane is unstable, it seems like it's going to crash. If the error of our robot is unstable, it means it's going to increase. We're going to have less and less accurate performance. Eventually, assembly line is going to not work, or whatever else our robot is doing, like the painting job is going to be off, etc. So stability is a necessary requirement. But just because we are stable doesn't mean that we are doing our best. For example, the error can go down to zero very fast or very slow. Let's say we can decrease our error by 20% in 60 seconds, or in 10 seconds, or in 1 second, okay? Completely different performances, right? If it takes 60 seconds to decrease error by 20%, that is maybe good enough for airplane, but not necessarily good enough for a precise pick and place operation, right? If we have to wait 60 seconds for us to kind of like get the error down by 20%, doesn't sound great. Doesn't sound great. So it is reasonable to ask a different question from stability. In fact, we can formulate the question quite directly. We can ask, how can we do the best we can? How can we do the best possible control? That is a question of optimality, all right? Previously, we were talking about stability. Now we're talking about optimality. So the best possible control, of course, implies stable control. We cannot be unstable and optimal, right? There is nothing optimal about being unstable. But out of all stable controls, we can pick one which is the best of all possible. Right? That is the topic of today's lecture, okay? Optimality. Okay. So let us consider a dynamical equation as the way I've wrote it here. For now, we don't say anything about linearity, but we'll get to it later. So just a general equation, x dot equal f of xu. Okay. With initial conditions x of 0. Then we will introduce a little bit of notation. So we'll define control policy. So control policy, pi of x and t, is a recipe of how to get u when you know x and t. So the recipe, control policy is not a control itself, is a function basically. Whereas control is the output of the function, control policy is the function itself, right? Okay. Okay. Now, okay. Our question would be, our question today would be, how do we find the best control policy? Because we could formulate it as, let us find the best control, but we need to know this best control for any possible x and for any possible t. So somehow it feels misleading to talk about the best control. We want to find the best control policy. Of course, this is a little bit, this gets a little bit convoluted because the topic that deals with it is called optimal control. So unfortunately, everything here is convoluted. But just remember, we are talking about finding best control policy. Okay. All right. So the best function of x, which would suit us. Okay. Okay. So if we were thinking about linear control, where control is u equals to k times x, then the question would be, how do you find the best possible k? That would have been the topic for finding the best control policy. How do you find the best possible k? Okay, all right. Okay. Now, to talk about something being best or being worst, we have to talk about something that we call cost function. If you are familiar with machine learning, in machine learning, we talk about reward function. So in machine learning, we want to have the maximum reward. In optimal control, we talk about cost function, and we want the smallest possible cost. So in machine learning, it is the maximum reward. In optimal control, the smallest cost. Same thing, but different sign. Okay. All right. Now, we will talk about specifically additive cost. That means that on each time step, we are going to only add to the cost. We are not going to multiply the cost or anything like that. We are going to only add to it. Okay, that is quite important. Is critical for all subsequent mathematics. Okay, so it is additive cost. Now, the cost function will be defined like this. It is a cost function depending on initial conditions and control policy. And is defined as integral from 0 to infinity, so from initial position to infinity, over some instantaneous cost by dt. Okay. Over instantaneous cost. So this guy, instantaneous cost, is something we are going to choose. Something we are going to choose. Now, notice that this cost, of course, depends on the initial condition instead of the whole trajectory x of t. Since this whole trajectory x of t depends on initial condition and control law, right? So control policy, control law. So we don't need to explicitly say that g depends on x of t because x of t itself is a function of pi and x0. So, okay, all right. Now let's g star be the optimal, so lowest possible cost. So g star would then be a function of initial condition, and it will be given as infimum minimum, okay, over pi of j of the cost, j of x0 and pi. So given all possible control laws, the optimal one is the optimal one is given as this infimum. It will be defined as j star. So the optimal control, the optimal cost would only depend on initial conditions. It cannot possibly depend on the control policy because we defined it as the best one over all control policies. So there would be some optimal control policy that had to be chosen to obtain this optimal cost. This optimal control policy will be called P star, right? So notice what happens. We initially define some kind of cost. Then we say out of all possible costs that we could have, there is an optimal one. It is a one and only cost, given some initial conditions, of course. Like different initial conditions, different cost, okay? But this cost, to attain it, we had to choose a specific control policy, okay? Specific control policy. This control policy is one and only one. I mean, there could be like a family of equivalent control policies, but let's not go there. Okay, one only one control policy that gives us this one and only one cost. Okay, best cost, best policy. And that sort of eliminates a lot of stuff. So trajectory, as you saw, was eliminated because it depends on policy and initial condition. Policy was eliminated here because we replaced it with the optimal policy. So that's like sort of this progression of, as we go towards optimality, more and more things are kind of fixed, right? In the end, optimal cost depends only on initial conditions. Okay, all right. By the way, the fact that it depends on initial conditions should be obvious, right? Let's say that the cost is how far away we are from the goal, all right? Let's say the goal is for the robot to pick an object, right? Like we have an object here, we pick it, right? So we pick an object. So we have to be in this pose, okay? If we are already starting in this pose, it automatically implies that the cost will be zero, right? Like we don't need to do any control actions. Our position is already at the desired state, so we don't need to do anything. So our cost will be zero. But if we start a little bit away and we need to move, the cost will be not zero, right? And if we start very far away, obviously we would have to move quite a bit. The optimal cost would quite obviously be even higher, right? So somehow it makes perfect sense that the cost would be a function of initial conditions. Okay, all right, the optimal cost, right? If I have any questions, please stop me at any time. Ask. Do you have any questions about this?
No, so far it's
Yes.
no.
No? Okay, good. Just stop me at any time. This lecture is conceptually difficult. Mathematically, it's quite easy, but conceptually, it's a little difficult. So just stop me as soon as you have questions. Okay. So we have, yeah. So with that, what we can do is we can formulate optimality conditions. So here we just discussed this, like, there's a cost, there's optimal cost. Now we could have optimality conditions. When is our policy the best policy? When is our cost the best cost? Okay, the optimal one. So for that, we need optimality conditions. Okay, so here they are. I give them sort of without a proof, just present for you the final result. That is called Hamilton-Jacobi-Bellman equation. Hamilton-Jacobi-Bellman equation, HGB. And it looks like this. So let us look into this equation and see how it works. So what we have here is minimization over U. So we minimize over control, okay, of instantaneous cost. So this is instantaneous cost plus derivative of the optimal cost with respect to x times f of x. This may look like a complete random collection of expressions. Like on the first glance, it looks like we just put everything into the salad. But let me give you a little bit of intuition how you can think about it. It is intuition. I'm not giving you mathematics right now, just intuition. Okay, let's think of what this reminds us of. Well, first of all, clearly this is x dot, right? This is x dot. Yeah, it's x dot. So we have dg dx times dx dt, right? So somehow this whole expression now looks very much like a chain rule, right? We wanted to take a derivative of g with respect to x and then of x with respect to t. All right. If you're familiar with multivariable calculus, you may be familiar with directional derivative. It also looks like a directional derivative. Or maybe if you remember differentiation with respect to vector fields, where you have a vector field and you differentiate with respect to it, right? You can say, okay, this is a function of a vector x, and there is a vector field like dx, x dot defined on x. That is also the same thing, right? If you're not familiar with any of this, doesn't matter. It's okay. It's not required here. But at least it should remind you of the chain rule, right? It is the dg dx, dx dt. Okay. Now, what is this? Well, let's go one more slide before and notice that j is a function, is an integral from 0 to infinity of g, right? g dt. So you can imagine if you take a time derivative of j, time derivative of j, you would get g, right? That's what you would expect. If you get time derivative, you would get g. Okay. Now, if you want, you can try to imagine that this is a partial derivative with respect to time. So it is like dj dt, and this is dj dx, dx dt, right? So the classical chain rule, take partial derivatives with respect to all variables until you get to independent variable. Okay. So this whole expression looks very much like just an attempt to take a full derivative of j star. I'm not trying to give you mathematics here again. I'm just trying to make sure you understand that this is not a completely random collection of functions. Like it somehow makes sense. Okay. Now, this, you have to minimize it with respect to y. So basically, you want this expression, but you want to minimize it with respect to with respect to u. You want to find the smallest possible expression with respect to u. U, of course, is a function of time, or just like a function in general. And this minimum with respect to u has to be equal to 0. Okay. So this minimum has to be equal to 0. All right. Now, the optimal control law will be given as u star, which is the same, just argmin over this expression. So the difference between mean and argmin is very simple. Like this gives you the value, right? The value of this expression. And this gives you the value of the argument of this expression. So the minimum of this expression would still be 0. It is just that we are getting the value out of this expression. Okay. You would often find in the literature the whole thing expressed this way, but it's basically it is the same statement. It's just that in the expression 5 we are talking about what the minimum is equal to. So we are giving the condition of optimality, whereas expression 6 is the recipe of how to get optimal control law out of this condition of optimality. Both are Hamilton-Jacobi-Bellman equation. Okay. So far, still, I'm sure it is a little bit mysterious, all of this. It's okay. It's fine. It's going to be less mysterious in next slide. So let us consider our familiar LTI. So x dot equals to ax plus bu. So much more close to home. Here we understand everything. So let's work with it. Let us, as the instantaneous cost, choose a quadratic function. So it will be x times q times x plus u times r times u. That is both of those are quadratic functions. So it is a scalar. Expression 8 is a scalar, of course, quadratic form. Hope you're familiar with how like mathematics here works, right? Like this is a row vector, this is a matrix, this is a column vector, right? You multiply, you get a scalar. Okay. When you substitute all of this into Hamilton-Jacobi-Bellman, what we get is instantaneous cost appears here, right? Then you have dj dx times f of x, but f of x is ax plus bu. Right? So almost everything except the instantaneous cost, except the optimal cost, is somehow quite clear. Like all of this is quite clear. It's just that we don't know what is J star, what J star is. Everything else we understand. Okay. Let's move on. Here comes a theorem. Same as Hamilton-Jacobi-Bellman came from somewhere. I did not give you a proof. I will leave it for you to study it, trying to find a proof if you want. Same, I will bring one more theorem without a proof. All right. This theorem says that optimal cost to go has a form of a quadratic, is a quadratic form of x. Okay. Optimal cost to go is a quadratic form of x. Okay, without a proof. In the second part of the lecture, you would see something that is a little bit would remind you a little bit of the proof for this thing. It is a reasonable thing to assume, right? That I would show you in the second part of the lecture. But without a proof for now. Optimal cost to go is quadratic form of x. Okay, okay. Notice no integral here. It is just a quadratic form of x. So you can imagine it is a quadratic form of initial conditions if you want to be very careful. Okay. But now we can take partial derivative of this guy. Partial derivative of this guy would be equal to, if we want to take partial derivative of this guy, it would be either like it would be basically something like this. X transpose C plus SX transpose. You can see those are the same thing, so it will be 2 times X transpose C. That is partial derivative of this guy. Now, here it is very easy to make a mistake. So here it's very easy to make a mistake. Namely, it is very easy to try to do this differentiation and substitute it directly into here. Substitute it directly into here. That is a very easy mistake to do. And then you would have like a little bit of a problem there. A little bit of a problem there. So yeah. What you should do here, I want to avoid going into too much mathematics since we're not going to actually use it in practical, like in the rest of the class. So I want to limit it. I apologize if it is too limiting. But what you want to think about here is basically that the way you want to think about this is the following. So you have this expression, right? G star. G star. You want to take a derivative of this guy with respect to x over a vector field, right? Over a vector field. So over vector field dx dt. Okay. So derivative of this. Basically, let's just take time derivative of this guy first. Let's just take time derivative. So the way time derivative would work here is it would be dot x transposed times c s, sorry, times x plus x transpose s dot x, right? So that is a time derivative of this guy. But now what we want to do is we want to replace all of those dot x with the expression for dot x, which is ax plus bu, right? So that is what we're actually trying to do when we are taking this dj star dx dt. So we want to replace those. So that is why the expression looks the following way. You would have, instead of this, you have this, right? And instead of this, you have this. Okay. So we get our familiar x times q times x plus u times r times u plus x transpose s times ax plus bu plus ax plus bu, right? Times sx, right? So that is the situation with this derivative, right? I understand that this is not the most basic derivative you ever took, but I think it somehow makes sense when you look at it this way, when you just try to take time derivative of this guy. Right. Okay. Now, we can simplify this. How do we simplify it? Well, we can take x out, like we can identify this part, right? And this part, they're all just a multiple of x, like they're multiplied by x on both sides. So here we go. We can put them here. We can also like write this here as a function of x and y at the same time. And there's r just without change going down. Okay. So that's the expression we get. Any questions? All right. Just ask me if something's unclear. Mm-hmm. Now we have so what we want to do now is the following. So oops, sorry. So we have this expression, right? But we remember that we have a minimum over u here. How do we find the minimum of a function? Well, a function attains a minimum at the extremum, right? At the extremum. So we want to find a condition for the extremum of a function. Extremum means the gradient is equal to 0. So the derivative is equal to 0. So if you draw a function, let me try to do it a second. If I draw a function like this, right? Okay. So it's at the extremum, its derivative is horizontal, right? So it doesn't grow anywhere. It just stays where it is. It just stays where it is. Okay, that's a necessary condition for the minimum. Okay. Okay. So we want to take a derivative of this guy and set it to 0, right? That would give us a minimum of u. Okay. So derivative of this guy. Okay, sorry, one more time we'll go back. How do I take derivative of this guy? Well, clearly it would be 2RU, or better said, 2U transpose R. Why? Well, because let's say we take derivative with respect to U, we get U transpose R, right? Okay, this is a symmetric function. So once we take derivative of the over U transpose, you expect to have the same thing. And you are going to get the same thing. It will be 2 U transpose R. If you wanted to understand how to take derivative with respect to U transpose on a more technical level, I mean, my recommendation would be to try to look into, basically, like, the best way is maybe to first expand it as a scalar, take derivative with respect to U, see what you get. That is the first recommendation. Second recommendation, try to write it all out in vector forms and try to understand what you're doing when you take derivative with respect to U transpose. But if you want just a recipe, when you take a derivative of, let's say, U transpose matrix, right, with respect to U, you take derivative as if it was just U without a transpose, and then you transpose the result, right? Then you transpose the result. Okay, so yeah, that's why you would have 2 U transpose R as a result of your differentiation. Here, this guy will disappear when we take derivative with respect to U. And this guy will become, I guess, let me just write it out here. So this is 2 U transpose R, okay? This is just 0 when we take derivative. This is X transpose SB, right? And this is the same. How to say it? The reason it is the same is, again, I can argue simply from like some kind of symmetricity. But if I take derivative with respect to U, I would have B transpose S times X, all of this transposed. So all of this transposed becomes X transpose SB. S, remember, is symmetric. S is symmetric, so that is the reason why it works. S is symmetric. All right, so we expect to have 2UR plus 2 SB equals to 0. That's exactly what we have. It's exactly what we have. Now, from this, we can express U. How do we do it? Or we get rid of 2 first, right? 2 goes away, divide by 2. Then we transpose the whole equation. After we transpose it, we get R U. R is, remember, symmetric. I didn't say it explicitly, right? It was on the slides, but I didn't say it explicitly. R and Q are symmetric matrices. Because the matrices that define quadratic forms for the cost, it only makes sense to make them symmetric. If they're not symmetric, we can always decompose them into 2 components. One symmetric, another one is skew-symmetric. Skew-symmetric will have no input on the cost, so we'll keep symmetric. In fact, we define them always to be positive definite, because if we define them as something else than positive definite, it will become possible to get infinitely negative costs, which we don't want. So yeah, it is, they have to be positive definite and symmetric. Yeah. All right, after we transpose, we get R times U plus B transpose S X equals to 0. And from there, the next step is quite simple. We we put all of this to the right-hand side with a minus sign. and multiply it by R inverse. That's it. That's it. So what we obtained, this guy, is called linear quadratic regulator. Linear quadratic regulator, LQR. This might be the first time you heard this term. Might not be, but for some of you, it is possible. So this is a very special moment, especially if you are going to do anything related to robotics or control. This is right now is a special moment in your life, if you didn't hear this name before. Because LQR is one of those things which is like ubiquitous. It is everywhere. It is something you're going to hear of again and again and again. It is one of those things which are default choice for people to use for all kinds of tests or performance comparisons and so on. The reason is because it is so easy to do. It is so easy to use. If you have a linear system, it is extremely easy to use. Basically, usually one line of code gives you LQR. And it is optimal. As I said, this result right now has given us the best possible control policy for our system. The best possible control policy. Notice it is also does not depend on initial conditions. It depends on X, on current X. That is, in fact, like there is an interesting connection you can think between initial condition and your current state. You can say, couldn't we treat our current state as initial condition for the rest of our trajectory? There is some kind of relation. So you basically what you get is just an optimal control policy, which depends only on your current state. And the next step also depends only on your current state. So you get this recipe of how to cook your best U. And it is just a recipe says multiply X by this matrix. That is all there is to it. All there is to it. Extremely simple. Linear cost. Linear control law. Is very nice. That is why people like it. The performance is nice. It has good characteristics which people understand. Yeah, it's like very little not to like about it. That is not to say that people use it for all practical applications. In practice, you often can do better, which is funny because we are talking about optimal control. What do I mean by do better? We'll maybe discuss later, okay? It is not universally used in practice, is what I'm trying to say. People sometimes use something else, okay? But as a like a default choice for quick test or quick comparison, this is extremely far, used extremely far. Okay. So LQR, your first meeting. Now we can rewrite it in this way, where K would be equal to this control gain. All right. Let us just look for a second at how this K looks like. Well, it is proportional to this C, which is the optimal cost to go. Basically, the C is somehow like a gain weights, which define which component of X influences the optimal cost more or less. All right, let's leave it. Okay. What is this B? B is our control matrix. What it says is our ability to go, our ability to influence a derivative of X given this U, this part of derivative would be this much, right? So here, optimal policy depends on this B matrix, right? So it takes into account how much influence you can have on each component of X given each component of U. Okay. And finally, you have this R inverse. R is, remember, your cost matrix on your control actions. So the cheaper your control action is, the more happy your LQR will be to give you this U. So for example, if R is equal to, let's say, diagonal matrix with components 1 and 100. So the first component is very cheap for your U, and the second component is very expensive. It means that inverse of R would be given as dag of 1 and 0.01. So it means that your U matrix here, its last component will be scaled down way much. So you're going to have much less of your U2 compared to your U1, right? So this is a scaling matrix that takes into account how much you hate to use one of your actuators, right? So somehow it feels sensible. It is not just a random piece of mathematics. This part of LQR feels sensible. Okay, the only question we have is how do we get S? Like we don't know. How do we get S? That we didn't answer so far. Let's look into it. So we substitute back our U into our equations. So remember this part, we isolated it previously, it only depended on X. Okay. This was our, again, part dependent on X, but then we had this this was our U. Let me be careful, sorry. Let me be careful, I'll get rid of this. So this was our R times U transpose and U, right? Those are U transpose R U. That is what we are seeing here. Okay. Now this guy is X transpose S B times U again, right? Well, so this is U. And same here, this is U times B transpose S X. Okay. That is what we see here. We substitute U back into our equation. Okay. Now let us do the following. First of all, we notice that this goes away, right? This goes away because we clearly have like a matrix times its inverse is just identity matrix. After it went away, this whole thing started to look exactly the same as this whole thing. And this whole thing, all of those three expressions are exactly the same. It's just the same matrix. So it is 1 times this matrix minus 1 times this matrix minus 1 times this matrix. So essentially what you can say is when we sum it up, let's say that this will cancel with this, and you're going to only have this last remaining. So this is what you'll get. That's the only thing that remains. Okay. So those two cancel, and you get only this last one remaining. Okay. So after all of this canceling terms, you get this part, and you get this part. So this part, this part. That is your final kind of like result for your HTB. So now what we need to do is we need to make sure that this whole thing would be equal to 0. Notice we can drop now minimize over U because U is not even part of this equation anymore. So we can drop it, right? But it still have to be equal to 0. So quadratic form would be always equal to 0 only if the matrix of the quadratic form is equal to 0. So instead of saying the quadratic form is equal to 0, we say the matrix of the quadratic form is equal to 0. Okay. What we got is equation 16 that is called algebraic Riccati equation. Algebraic Riccati equation. That is an equation which you can solve in order to find your S. So the matrix S, you can find it by solving algebraic Riccati equation. That is a quadratic equation in S, but there is a good part to it. It's there is algorithms to solve it. It's very easy to solve. I could tell you how to do it like in a principled way. Like there is a nice way to think about how you can solve those equations, but it would require us to go into a little bit of a different area of mathematics, which I don't want to. So for now, I just say it is possible to solve it numerically. And the way you can do it is, for example, by calling a LQR command in MATLAB. You call LQR. You give it as parameters your matrix A, B, Q, and R, and you get your gain K, your optimal cost to go S, and some parameter P. Okay, let's not go into detail what it is. Just okay. Or okay, P is this guy. So it's your eigenvalues. Or in Python, you can call scipy linalg solve continuous algebraic Riccati equation, ARE. Good to know that ARE usually means algebraic Riccati equation. And again, parameters are A, B, Q, R. And you get your optimal cost to go S. So in Python is not going to give you K. It's only going to give you S. So you have from your S, you have to get your K. All right. So the Riccati equation can be solved numerically. There are principled ways to do it, but for now, let us just think of it as a recipe of which we work with it by calling a function somewhere. That is normal. That is not something that is, how should I put it? You're not losing anything by doing it, right? That is not one of those cases where you should have done it by hand, but instead you did it by calling the computer. It is bad. No, it's not one of those cases. That you do not lose anything by doing it this way. Okay. Do you have questions so far? Do you have questions so far?
Oh, yes.
Oh.
Could you please explain in the name of this method, linear quadratic regulator, we have quadratic, but what does it mean, quadratic?
Okay. Good question. Good question. Sorry, I did not illuminate. So the reason we call it linear quadratic. Linear because it works with linear functions, right? Linear dynamics, LTI. Quadratic is because it works with quadratic cost. So quadratic cost XQR, XQX, right? That is URU, quadratic cost. So both of those are quadratic forms. And the linear quadratic regulator is basically optimal controller for linear dynamics with quadratic cost. That is linear quadratic regulator. The name is is confusing. Linear quadratic. Yeah, it's a good name. What can I say? Good name. But is very classic. It has been around for a very long time, so it's going to stick. Yeah, linear quadratic regulator, linear dynamics, quadratic cost. Even the word regulator, it might be familiar to you if you studied in like Russian technical school, because that's what in Russian we call controller. Controller in Russian is regulator in classical old school terminology. But in English medium, the word regulator almost completely went out. So now we call it controller. But the name contains this old reference to how controllers used to be called regulators. So it's a linear quadratic regulator, even though it is basically optimal linear control.
Okay, thank you. I see.
Yeah. No, thank you. It's a very good question. Any other questions? Okay. All right. Let's move on. We have half an hour, and I want to give you a last chunk of this lecture. It's going to be a little bit simpler. So from this part, like this part of the lecture, what is critical is for you to understand Riccati equation, right? That's critical. You need to understand like this equation, that you know what it means, right? The recipe for getting this optimal cost to go matrix. It is also critical for you to understand this recipe for computing optimal u given x from optimal cost to go function. So like this idea is critical. You need to understand where R and Q came from. So like from here, right? Optimal cost, right? But that is it. That is it. So it's just understanding. In terms of mathematics that you're going to do in your practical life, this most likely will be this. You just call a function. You know, it's very easy. But on the exam, I might give you a question which would be easily solved if you understand, like if you understood this derivation, like this derivation, this derivation, this derivation, or if you memorized equation 16, for example. Yeah. So on the exam, I might test either your memorization of 16 or your ability to derive. You know, one of those. Okay. All right. But ultimately, again, what I want to say is, like this, calling this LQR just gives you all of this for free, more or less. Okay. Now, all of this was for continuous time dynamics, but we can do it for discrete time as well. So let's do it. All right. Before we go, just last comment, and then we go into discrete time. So you might already have seen ball placement in your practical sessions. So ball placement is an alternative to LQR. Basically, for undergrads, there are two types of control designs that you use: ball placement and LQR. If you had like robotics course, you would also know PID design. But in control theory, it is usually ball placement and LQR. All right, ball placement, it has positives. This positive is that it allows you to design exactly what eigenvalues you want. So exactly how fast something goes to zero, right? You can design if you're going to have oscillations or not. Ball placement gives you exact control over all of this. The negatives is it may require unreasonably high control gains. So you may ask, okay, give me eigenvalue -2. It would give you eigenvalue -2, but your control gains would be tens of thousands. So completely impractical, something that is impossible to do in practice. All right. And let's say you would say, okay, give me some eigenvalues that would not give me those control gains. Well, ball placement does know how to answer this question. You have to ask reasonable questions when you work with ball placement. You cannot expect ball placement to give you a hint which eigenvalues are good or which are impossible. Right? Okay. Now LQR upsides. Whatever cost you give, it will give you the best control gains for this cost. If your cost is at least somewhat reasonable, what I mean is your Q and R matrices are, in terms of magnitude, orders of magnitude, correct. You will get reasonable control gains. So it's not a question of if eigenvalue should be -2 or -2.5. It is a question of should Q be, for example, I'll just write it here. Should Q be given as, let's say, identity times, let's say, 100. All right. Is that reasonable? sorry. Okay. Q identity times 100. Right. Right. Or can I, for example, do it as identity times 10 times 10, right? Or maybe identity, just identity, right? Without like any coefficient. This is a level of coarseness LQR allows you, right? You can work with orders of magnitude rather than with like digits. In practical tasks, you would still have to go back to digits when you fine tune, because like every time you have to like go into detail. Practical work does not allow you to relax ever, right? You cannot expect something to just work like this in 5 minutes in practical tasks. But in tests, where you just want to quickly understand if the system is working well or not, you can get away with just this. Like you would say, okay, let me design a controller. I will say Q is equal to 100 times identity. Probably will work on the first try. If you don't like on the first try, you like change it 10 times smaller, 10 times bigger. For tests, this often works. Again, this you cannot deploy it to actual practical robot like this. But for tests like numerical stuff or simulation and so on, this often just gives you good enough stuff. Okay, that is the plus side. Downside, it is very easy to produce something that is has bad eigenvalues, like decay is very slow sometimes, or something else happens, like oscillations appear. And the LQR does not give you a recipe of how to combat those. Like, there is no specific way of saying no oscillations, please, no oscillations. You cannot do this. Right? So, two methods, very different, have different upsides and downsides. Important to realize the difference between the two. Okay. If you have questions. All right, let's try to go through a discrete case. So let's see our familiar, hopefully, discrete dynamics. X I plus 1 is equal to AXI plus BUI. Okay. The cost function here would be given as quadratic, but now it is not integral, it is a sum. It is a sum. Okay. So we want to find optimal control policy here. Okay. I apologize for the typos on the screen. That was unusual. I did not have time to clean it up yet. My apologies. Okay. So let's think about the cost function, what happens. We need to sort of study it a little bit here to understand where we are going. Here is with the discrete dynamics, it is a little bit more important to understand this whole thing with cost to go. So first of all, let's just assume that we are going to have a linear control law. Let's just assume. We're going to drop this assumption later, but it's let's just assume this. If we call our initial condition Z, then we can find, given x0, we can find x1 as a function of this initial condition. So x1 will be, a x0 plus b u0, but u0 is equal to minus k x0, so it is minus a minus bk x0, which is z. Okay. Now, let us define components of the cost associated with each iteration. So G1, J2, J3, and so on. So in each iteration, we have J1 is equal to X1, Q1, X1 plus U1, R, U1. Okay. Now, during the first iteration, we know that u sub 0 is equal to minus kx sub 0. So we can show that the first component of the cost, g is 0, would be equal to, so x0 times q times x0, so z times q times z, okay, plus u0 r u0, which is k times x, right? So it is z times k times r times k times z. Okay. So it is basically a function of initial conditions. And as we move forward, we're going to see exact same thing. As soon as we chose control law, what we'll find is that each of those j's will be a function of initial conditions, as you would expect, right? It's always going to be a function of initial conditions. Okay, all right. So it's a function of initial conditions. So each of those cost components will be a function of initial conditions. Okay. And not only it is a function of initial conditions, by the way, it is a quadratic function of initial conditions. Remember what we were talking about, that theorem with optimal cost? Well, if any cost can be expressed as a function of initial condition, as a quadratic function of initial condition, well, obviously the optimal one is also going to be expressed as optimal, as a quadratic function of initial condition, right? So in this case, at least, when we are talking about discrete systems, it is kind of obvious that optimal cost will be expressed as a quadratic function of initial condition. Okay. Now, let us define cost to go as optimal cost for given initial conditions. Right? So the exercise we already done once for continuous systems, but now for discrete systems. So cost to go is a cost, optimal cost, right, for given initial conditions. So it is minimum over u of this sum. Okay, minimum over u over this sum. Now, right. Now, if we have trajectories that looks like x0, x1, x2, and so on, like a sequence of points, we can define optimal cost to go from each of those as from initial conditions, right? So we can say v0 is a cost to go from x0. v1 is a cost to go from x1, and so on, right? And we remember that all of those will be quadratic forms of x, of initial conditions of x. Right? Like it has to be. They have to be quadratic forms just because discrete dynamics always produces us those quadratic forms we showed on the previous slide. All right. So we have this sort of just definition like optimal cost from initial condition, optimal cost from x1, and so on. Okay. Now, again, remember our notation. We now also define u0 as omega, W. Now, what we can do is we can write our cost to go from the initial position, v0 of z. And we will define it. We don't have to define it. We basically just write it out as minimum over w of zqz plus wrw. So this is a component of the cost associated with the first iteration, right? Plus v1 over, v1 as a function of the next step, right? Let me explain it a little bit more in detail. First of all, what is this? This is basically x1. Well, this is basically x1. Okay, if z was x0, this is basically x1. Okay, okay. All right. Now, what is this? This is basically our G0, J0, right? It is the cost associated with the first iteration, J0. So what did I say here? I said that the optimal cost to go on the 0 step is the same as the optimal cost to go on the second step, on the first step, so on the next one, right? Plus the costs that we incurred while doing this step, right? So we are at the 0 step. There is a step number 1, so next one. What is the difference between those two costs? Well, the costs that I incur while going from the 0 to the 1, right? So this first step, the steps they make here, is the cost associated with it is the difference between those optimal costs, right? Okay. But the thing can be written the way I wrote it here. So the optimal cost as a 0 step is the same as optimal cost as the step number 1, plus the cost that I incur while doing the step from 0 to 1. Right? Okay. Good. Now this is called Bellman equation. Hamilton-Jacobi-Bellman is usually continuous time equation. For discrete time, you can call it Hamilton-Jacobi, you can call it Bellman. There are options. Bellman, I think, is a more popular one. We also sometimes call it I call it a dynamic programming, like optimality condition from dynamic programming. Yeah, there's just ways and ways to call the same thing. All right, but of course, Bellman equation would have like I here and I plus 1 here. Right? It would be like previous equals to cost on the current iteration plus the next cost. So it would be more general. But yeah, it's a Bellman equation. Okay, all right. So far, this is kind of trivial, so I don't want to give it impression that it is something profound. We're just saying that cost that we incurred if we go the whole way is equal to the cost of the first step plus the rest of the way. That is all there is to it. Okay. Now, here is when the fun starts. We know that V0 is equal to x0, like initial x, times p times x, right? And V1 is equal to x1 plus p1 times x1. All right. So again, we use our our substitution variables, like we just call x0 z, right? So we have v0 instead of v0 we put its expression here, z p0 z, and instead of v1 we put this x1, okay, x1 p1. Let me put it more clearly. Okay, so this guy is here. This guys are here. Yep. Here's P1. And the rest is just a part of Bellman equation. So Bellman equation becomes like on the left-hand side, I've wrote what V0 is equal to. On the right-hand side, I've wrote out what, just expressed out what V1 is equal to. Now we can find minimum over W over W. How do we do it? We take derivative of the right-hand side with respect to W and equate it to 0. For the same reason, we need extremum of this function, and it should extremum is derivative equal to 0. So we do this. So derivative of this is 0, of this is 2W transposed R. and derivative of this is AZ BW transpose P1 times B. Oh, and 2, I forgot 2. Here it should be 2. Okay. 2 in front of, let me do it correctly. In front of this brackets, it should be 2. Okay. You then you do the same exact thing as we did before. So you divide by 2, transpose the whole thing, put then you open the brackets, you collect everything in front of B in the brackets, right? Put everything in front of Z into the right hand side. Then you multiply by brackets with inverse, and you get expression for W. Right? Just in the interest of time, I will avoid giving step-by-step instruction of how to solve this for W, but this is the final expression. Right? This is the final expression. There is nothing magical about it. It's quite clear. Like the only step that is not completely obvious is transpose and then collect everything in front of W in the brackets and then multiply by it. Okay. Now, by the way, you might be worried that this expression might become degenerate. Well, it shouldn't become degenerate, and the reason is because this matrix is positive definite. This matrix is positive definite. Multiplying positive definite matrix by a matrix which is full column rank, sorry, full like conjugating basically like this is full. This matrix would have full column rank. This has full row rank. It's the same matrix transposed, right? So basically, multiplying it like this preserves positive definiteness. So this is positive definite plus this positive definite. Their sum has to be positive definite. Their sum cannot be semi-definite or anything like that. So this matrix would have to be invertible. Yeah. There is no problem with it being not invertible. Okay. So, and what you have here is the optimal control law. So basically this is your LQR gain. But now for this discrete case, you can see it is a little bit more ugly. There is a little bit more stuff here. It's not very bad though. And actually, if you tried to make it more pretty, you could. So, but ultimately, it's just like a bunch of matrices. So is it very bad? No, it's not. Just a bunch of matrices. That's all. Okay. So in general, you can see that U sub I would be equal to minus this whole matrix times X sub I. Okay. Fair enough. That is what we would get here. All right. Now, what we need is to find a control update for P, right? We need to know how to compute P. Here, the trick is that instead of computing P by solving Riccati equation, algebraic Riccati equation, as we did before, the way people do it here is they generate an update law. Basically, it relates previous P0 to the next P1. And like, so P sub I to the P sub I plus 1. How do you do it? Well, you just take this equation, substitute into it your V, which is what you got here, right? And you get a huge quadratic form, which has to be equal to 0. A huge quadratic form that has to be equal to 0. That is what I wrote here. this basically means the same thing as on the right-hand side, but transposed, right? So here again, it's like the same thing as on the right-hand side, but transposed. Okay. And you can substitute it, you can solve it. There would be a little bit of algebra, and then it would there would be like a shorter form of Riccati equation. It would be what we call DARE, discrete algebraic Riccati equation. It would basically give you a recipe of how to find your pi given pi plus 1. This motivates like a way to compute your gains. What people sometimes do is they define some final cost to goals that they want to achieve, and then they find all previous costs. Like, let's say you define your final cost, and then you say, okay, from this I can compute the cost previous to the final, and then previous to the final, and then previous to the final, and so on. That is one way to kind of like interpret this whole thing. Another way to think about it is people would say, okay, well, here's my final cost that I want to achieve. I would iterate backwards using this equation, and it would converge to some kind of situation where my previous p sub I and my next p sub I would be the same. So I will basically achieve convergence, and I will use this convergent value to do my control gains. There are ways people do it. I don't want to go into these details, but especially since you're probably going to, again, use software to do it, like you're going to call some kind of software to get you to solve your discrete algebraic Riccati equation. And then you would either get control gains, or you would get your matrix p sub I from which you can compute your control gains. It depends on what function you use. But what I wanted to show you is that it is essentially the same process as before. But here, we, rather than doing those theorems, which I remember with the continuous case, I told you there are two theorems. One, Hamilton-Jacobi-Bellman equation. I did not tell you where it came from. I just said it is here, it is correct. Okay. Second, I gave you a theorem that optimal cost to go is quadratic, right? With those, we can do complete, a very easy derivation of Riccati and LQR. With discrete case, we don't need to do this like believe in the theorem. We actually derive it quite clearly. All right. So somehow often we think of continuous case as a let's say a more complicated version of the discrete case, right? Discrete case is considered to be a simpler thing if we want to derive everything, right? Yeah. So if you want to understand a little bit better the optimality conditions, I would recommend you to start with discrete case, because it requires less of those like theorems and proofs. It's just all out there. You can see how, everything here was quite clear. Yeah, so it's I would recommend it. In all of those cases, there are quite a few details that we didn't mention. One detail is like we were integrating from 0 to infinity. What if we want to integrate from 0 to a certain time period? I was talking about LTI systems. What if the system is not LTI, right? And so on and so forth. Right? There are details, and those details will be in papers, in textbooks, in tutorials. There will be a lot of those places where you could learn more about LQI and Riccati. For our course, we're not going to cover those. It is sufficient for you to understand continuous time Riccati, how to use it, and to look and like have some understanding of discrete case as well. All right, but just be aware that this is like scratching the surface. Same as everything that we do is introductory course. Okay. With that, I think we're out of time. That is it. If you have questions, I will stop the recording and take them.